1,000 units to 10,000 units if for small batches, the number of containers will be the full batch. Once APS is carried out, the units should be agitated, swirled, inverted before incubation. All integral units from the APS should be incubated and evaluated. Included units used with cosmetic defects and those which has gone through non-destructive in-process control check. That means that even if these products are not part of the product which will be released, to have a perfect understanding of your process, you need to incubate them. That means that you can separate them from the rest of the batch, but you have to consider that as well. If you have some problem, for instance, ampoules are time to time difficult to be filled or to be freeze dried, you can have product falling and ampoules falling, something like that. You have to remove them from the process because uh, it's they have lost product or things like that. You cannot remove during the APS more units than what happened during the standard batches. So web process include materials that contact the product contact surfaces but are then discarded. Product flushes. The discarded material should be simulated with nutrient media and be incubated as part of the APS unless it can be clearly demonstrated that this waste process would not impact the sterility of the product. Field APS unit should be incubated in clear containers. So amber glass, opaque plastic are not allowed. If you cannot substitute, and for the APS, you will need to, as it is media, you will need to substitute this amber glass or other packaging materials by clear materials. Field APS unit should be incubated without unnecessary delay to achieve the best possible recovery of potential contamination. Field APS unit should be inspected by personnel who have been appropriately trained and qualified for the detection of microbiological contamination. So, inspection team to look at cosmetic defects or looking at particles, if they are not trained appropriately for detection of microbiological contamination, cannot be part of this team. You will need to train them. And after the end, you need to undergo a positive control. This point is really important. The target should be zero growth. That means that when you have one growth, then the APS is considered as failed. You need to carry out an investigation, determine the root cause, determination, implementation of appropriate corrective measures, sufficient number of successful consecutive repeat APS, they said minimum of 3, should be conducted in order to demonstrate that the process has been returned to a state of control. So a prompt review of all appropriate records relating to aseptic production since the last APS. So we have said that for the aseptic process simulation, for the aseptic processes, we will need to make some monitoring, a lot of monitoring. All this data, all this information will have to be reviewed and include into the risk assessment to see potential sterile breaches in the batch manufactured since the last successful APS. All products that have been manufactured online subsequent to a process simulation feature should be quarantined until a successful resolution of the process simulation failure has occurred. And where the root cause investigation indicates that the failure was related to operator activity, action to limit the operator's activities until retained and requalified should be taken. This is the reason why you should include in your disqualification of personnel this point, which is unsuccessful APS. Production should resume only after completion of successful revalidation. That means that APS is not the full validation, but it is really critical for our processes. When do we need to repeat the initial validation? It's when the specific aseptic process has not been in operation for an extended period of time, that means 3-6 months. There is a change in the process, equipment, procedure, or environment, but this will take place within the change management. Now we'll go into 2 case studies. So first, the problem statement. We have an aseptic process simulation for a full process of vaccine. So we need to prepare the vaccine from the viral growth on eggs embryo, bulk preparation for filling freeze drying in vials, closure of the vials. Filling line is conventional, lyophilizers, loading, unloading manually. The target is compliant APS with 0 growth. So we will need to carry out a risk assessment, and we will need to consider hazard which could impact. We have to consider that this is a manual process. We will need to assess that we have a room layout which is one direction process flow. The personnel will introduce risk of contamination. The process robustness is well not. Material, eggs, vial stoppers, media have to be considered as well, and we need to reduce the risk to an acceptable level. If we consider all this for the process, then we can move into the aseptic process simulation. For the process, we will start to decontaminate the eggs. Introduction in the grade A, B area. We will carry out a simulation of the eggs process, maybe filling vials with media and moving from one biosafety cabinet to another one, exit the eggs from the process room, carry out kind of incubation time, redo eggs disinfection, then move into the grade AB area and make the harvesting. Then if we have a freezing of our vaccine and storage at frozen temperature, then we will have to consider this point as a holding time and consider if we use the harvest media after a few days. Then we have several equipment. We have local protection, which is an HEPA filter within rooms which are not grade A or grade B. It could use to reduce the risk in any background classification because we have here a grade A air supply. Now, if we want to prepare some vaccine, we can have several biosafety cabinets connected one to the other with mouse holes and transfer of the product through the mouse holes and with a unique directional airflow. And this is something which could work. Then maybe the design could be improved if you have some risk of virus dissemination, and then keep the air going back to the equipment. This is something we need to consider during the design and the choose of this biosafety cabinet. Then we can go to the aseptic process simulation. So we have the vaccine, which is frozen. We have the vaccine thawing. We have to introduce sterile materials into an isolator, small isolator. We have prepared the buffer sterile, and we will make a sterile filtration. And this will go into a formulation in sterile tank. Then we have the formulated vaccine. We have stated that there is no sterile filtration because we have viruses and we cannot filtrate this product. So we have to make vial filling without sterile filtration, which make this system much more complicated. Then the machine will make the vials pre-stoppering, will go to the freeze drying operation. After the freeze drying, we'll have the final stop. We will put the stoppers in the final position, and we will go to the final vials crimping. All these operations have to be simulated during the APS. The point which need to be considered is here. So all the sterile activities here based on your risk assessment, and here the freeze drying, where you have to consider loading of the freeze dryer, putting the freeze dryer, closing the freeze dryer, going enter vacuum, maybe not the full vacuum, then break the vacuum with sterile air, put the stoppers on the final position, open the freeze dryer, and then move to the crimping.